Hello, calculus fans! So we've defined the triple integral over a rectangular box. We now have to define the triple integral over a general bounded region in three-dimensional space, a solid. And we're going to use a similar procedure that we used for double integrals. We'll enclose our solid region in a box and then define a function, big F, so that it agrees with little f on E, but it's 0 for points in the box that are outside of E. And then, by definition, we're going to say that the triple integral over E of little f is equal to the triple integral over the box B of big F. This integral will exist as long as little f is continuous and as long as the boundary of E is reasonably smooth. And for any function that we run into in this class, that certainly will happen. The triple integral is going to have a lot of the same properties as the double integral. Now, let's restrict our attention to continuous functions and simple types of regions, which we'll describe in a moment. So, in a direct analogy to what we did for plane regions, we're going to call a solid region a type 1 region if it lies between the graphs of two continuous functions of x and y. So that is, our region of integration, E, is the set of all points where x and y comes from some set D in the xy plane. And here's the important part. The values of z lie between u1 and u2. u1 is some function of x and y. u2 is some function of x and y. And D, that's the projection of our solid into the xy plane. Here's the picture. So you can see an upper bounding surface, a lower bounding surface, and then the whole thing is above some region D. The upper bounding surface is the surface with equation z equals u2 of xy. The lower bounding surface is the surface z equals u1 of xy. So we'll use the same kind of argument that we did with double integrals. We're going to get this integration formula. The triple integral of f over E will be the double integral over D. Remember that D is the projection of E into the xy plane, of the single integral from u1 of xy to u2 of xy of f of xyz dz. So the single integral on the inside, we evaluate that, and then when we're done, we get a double integral. So that inner integral means that we pretend that x and y are constant, and which means we also pretend that u1 of xy and u2 of xy are also constant. And when we do all that pretending, we'll integrate f of xyz with respect to z. There is one particular case that's important to recognize. That's when this projection, D, of E into the xy plane is a type 1 plane region. That's the picture that we see here. So if we can take the solid, project it down into the xy plane, and then get a type 1 plane region, that's a special case that we should recognize. In that case, we can express E like this. It's the set of all points, x, y, and z, where x goes between a and b, y goes between g1 of x and g2 of x, and z goes between u1 of xy and u2 of xy. And if we can express it that way, then we can write down the triple integral like this. It's the integral from a to b, that's the outer integral with respect to x, of the integral from g1 of x to g2 of x, that's the middle integral with respect to y, of the integral from u1 of xy to u2 of xy, of the function f of xyz, and that innermost integral is with respect to z. And then another possibility is that D could be a type 2 plane region. Here's a picture of a solid whose projection into the xy plane is a type 2 plane region. That means that projection has bounding curves which are functions of y. Here's how we can express E if its projection into the xy plane is a type 2 plane region. E is the set of all points x, y, and z, where y goes between c and d, x goes between h1 of y and h2 of y, and z goes between u1 of xy and u2 of xy. And then we'll write down the triple integral like this, and this time we're expressing the integral in the order of dz dx dy. Slightly different, same concept though. Okay, that's all for now.